we're finishing up yesterday with this question of the exceptions to the off-bow rule. So the copper and chromium exceptions. We talked about how what we would expect based on how the other elements in that row work, even in that transition metal row, would be that we'd have 2 electrons in the 4s, and then we'd have the 9 3D electrons in the 3D orbitals. But in fact, that's not what happens, because there is a great energetic advantage to having a full sublevel when we have these degenerate orbitals, and particularly when we have these larger sets of orbitals. So you don't see this with p orbitals, I think, partly because the difference between the s and the p is energy difference is big enough, whereas here the 4s and the 3d are like right on top of each other, kind of. So there's a lot more room for flexibility, and we're going to talk more a little bit later about these transition metals and what else happens with these crazy d orbital electrons, and why basically everything that has a color, every substance that has a color has a transition metal in it, because that's how we get color. So we'll talk more about that later. But that similarity here and this sort of energy bonus for having a full or a half full sublevel means that we're going to pull one electron out of the 4s in order to give us a very stable full 3D sublevel. And the 4s having 1 electron, not so bad. It's not. It's more better to have a full 3D than it is worse to have a half full 4s. I wanted to point out, though, I don't think I did in this class, but I did it. I'm just going to duplicate this page. So the same thing is true with chromium, because it's really close to having a half full sublevel. We're also going to yoink that electron that would normally go in the 4s, and we're going to stick it in the 3D. So we get that not quite as good as of a bonus as a full sublevel, but still a bonus being half full. But what I want to do is talk about just briefly why this doesn't work for something like nickel, right? So nickel is right next door to copper, so you think, oh, well, maybe this would make sense here too. So our electron configuration for nickel is 4s2 3d8. And we talked about how when nickel becomes an ion, it loses, like all of these transition metals, when they become ions, they lose the 4s electrons, because that is those electrons are more available to leave than the ones that are in the 3D orbital. And I was saying this morning to the IB1 class that this is totally not like scientifically correct, but as a way to think about it, because I love anthropomorphizing everything. You can sort of think about the 3D, when there's electrons in it already, it kind of like sinks down. It has a little bit of a weight to it, okay? And that brings it a little bit below the 4s energy, makes it a little bit less available. It has to do more with the shielding from the 4s electrons to the nucleus, and I don't want to talk too much about the details of why, but you can, once you have electrons in 3D, then it's easier to remove them from the 4s. But why doesn't nickel just take these 2 electrons and put them over here? Because, that would be giving it a nice full 3D sublevel. And the reason is that moving 2 electrons over and having an empty 4s is not energetically favorable. So it only works for copper and chromium because they are 1 away from this nice place. They only have to shift. I mean, they're not really shifting one electron. That's just where the electron is. But having just one in the 4s and then a bunch in the 3D works. Having nothing in the 4s, even having a full 3D sublevel, that's not going to work. Okay. So that does not happen. So it's only the chromium and copper groups that do that. And it does happen in other elements in those groups. You're just not required to know them because the IB, like the syllabus, only deals with the first row of the D block. Okay. Does that kind of make sense? Okay. I think I started this when the bell rang because I forgot what time the bell was ringing yesterday. So if we look at ions, so this is our neutral configuration for chromium. Okay, 4s1, 3d5. If we lose one electron, right, we're going to lose it from the 4s. So if it's a 1 plus charge, then this is going to be gone. Okay. You don't see a lot of that for chromium, possibly for similar reasons to why nickel doesn't work that way, although I'm not sure if that tracks with copper. Yeah, it doesn't really track with copper, so never mind that. But so the first thing that's going to go is your 4s, and then if it's a 2 plus ion, you're going to start losing them out of the 3D. Okay, so it's exactly the same as the other ones. Once you have the correct neutral electron configuration, it's exactly the same as the other transition metals in that you're losing the 4s first, and then you're losing them out of the 3D, right? So I'm actually going to, let's see, let me do this to make it a little bit more clear. So if this was, if this is chromium 2 plus, then we would lose the 4s, and we would have 4 electrons in the 3D. It is very unlikely. I don't think that they will ask you for copper or chromium ions. I just wanted to kind of come full circle on this with that. So you will be required to know copper and chromium neutral electron configurations and the fact that they are different, but you won't need to do ions for those, I don't think. But just wanted to point out that it's the same thing once you have the correct configuration. Okay. Questions on that? Okay. This is the last page in your study guide packet, and we didn't really talk about it because we've been doing this kind of all along. You can also show these box and arrow plots without the energy diagram, right? So you can just have them basically horizontal, and you'll see this for the smaller elements, like up to neon, basically, because once you have more than that, then it starts getting unwieldy. Okay, but you may see that these orbital diagrams done without an energy axis. So this would be our 1s. Helium, this would still be our 1s. For lithium, this would be our 1s and our 2s. Beryllium, 1s, 2s. And then for the rest of these, it would be 1s, 2s, 2p. Okay. And it's not a bad idea to just go through and draw these because it's a good reminder of, with the 3 on the bottom of the Hund's rule, that you're adding to the empty boxes before you double up. So you may want to do that. But I just wanted to point out that this is another way of drawing these orbital diagrams if you aren't using an energy axis. Okay. And that is all I have for this. So if you have any questions, or if you've tried any practice problems that you're not sure about, or if you want to go over what you did for the homework, now's the time. I gave you that practice worksheet because it's nice to be able to practice, so just do more repetitions, whatever. That is a complete as much of that as you want to, and give it to me on Monday, kind of thing. I would like your homework from yesterday turned in if you have it. We did the front in class, and you're supposed to do the back for the homework. If you have questions about that before turning it in, let me know. And yeah, that's it. All right.